Okay, let's get started. So as we all know, like humans, we are like a multimodal learners. So we can input different modalities such as we can read books, we can see images, and we can also listen music. We can also output different modalities such as we can talk, we can write words, we can also draw picture, draw like photos, images. What about AI? How do they process different modalities? So at the beginning, like people were trying some simple ideas on some simple data. For example, like Cloud Channel, it tried to output text like with some n-grams. And later in 1999, people started to study how to generate textures by predicting pixels. So basically, that's output the modalities, the text, and the pixels. And in the deep learning era, people start working on some complex data like the real images. So for example, we can understand images. We can also understand text embeddings. And with the introduce of the transformer architectures, people kind of not unified the texting and the text out like all the NLP tasks. And recent years, we can output the image as a modalities. And very recently, we have the multimodal models, or we can call it any-to-any models. So basically, any modality in and any modality out. Of course, because the most of the data is image and text, so those models just focus on the image and text, but conceptually, we can generalize to any modalities. So anyway, there is a very clear trend, like any-to-any models are coming. But one question we want to ask, like, are we ready yet? So in today's talk, I want to talk about two topics. The first topic is one model fits all modalities the best approach? The second one is, if models can understand everything, then can they also understand you? So for the first question about one model fits all modalities, let's look at how our human brain works. So how do we process different modalities? So for the human brain, we actually have different regions to process a different modalities, such as some region will process the spatial sensory integrations. Some part will process like a visual processing, just like vision encoders. And some can just process the audio or language. Some do the reasoning. So the feature of our brain is like we have a different regions to process the different modalities, but they are kind of deeply connected. For the second question about if the model can understand you, that's about mostly from the data perspective. So for nowadays, like our brain will receive a tons of data. The first part is what I call the general data. So for example, when we are young, our teacher or parents will teach you what is a dog, what is a cat, those kind of things. But on the other hand, we also interact with a lot of personal data. So what do I mean by personal data is the people or the objects surrounding you, and you have some like a unique meaning and a name attached to them. For example, suppose I have a dog named Max. When I play with a dog in the park, I will just say, "Oh, hey Max, come here." Instead I won't say, "Hey dog, coming here." So that basically also back up a recent not recent about Scientific American study shows people spend 60% of a conversation talk about themselves, and the number jumps to 80%. So that means actually as a human, like a multimodal learner, we are not kind of interact with a general data, at least we actually talk about a lot of personalized experience. So that leads to today's talk agenda, which is the first I will talk about how do we build a unified ML models, and then how do we personalize those models, and then I will talk about some open questions and future directions. So I will talk about the first part, introduce our work at Fusion, introducing new modalities to large language models. So a unified model is a really hot topic recent years, and people have been putting effort on these directions. And a unified model, like I introduced before, it refers to a model, single model. It can take in like any modalities, such as image and text here, and it can also output those modalities. And for text, typically people choose the autoregressive modeling. But for the image, people studied also use autoregressive, such as the work from last year, Meta, the comedian. If you try to model the image region with a diffusion, we also have some study. Basically, the transfusion work from this year, a clear paper. But one like a shared property for all those two work is they have a huge chunk of like a transformer to process all the modalities. And in this paper, we want to like argue, should we use the shared weights to kind of separate weights for different modalities? Why we want to do that? First, like it's like biologically, like our human brain like works like that. So basically, nature is our best teacher. So maybe we should also try that direction as well. And the second point is actually nowadays we have a lot of good models from different modalities. For example, we have a good language model. We have a good like image model. We also have other kind of modalities. So it would be nice we can think about like how do we use those pre-trained models and combine them together. So that motivates us have our work execution, introducing new modalities to the LLM models. So basically, in this work, we introduce our framework execution, which is unified ML models. So like any other ML models, which takes in the interleaved image text data. And for those input, of course, we will have some tokenizer or vision encoder to encode those input modalities into the tokens. And those tokens will be fed into our execution model. So unlike the transfusion or chameleon, which they have the single like transformer block, we have two, like we call the two towers. So one side is we call the language tower, which will primarily processing the language data, and another one is called the image tower. So they are kind of like the separate in terms of the model parameter weights. But because of it's a joint training, so they are kind of connected in their representation space. And of course, we can just model them like using different objectives, such as you can use autoregressive for text and maybe diffusion for the image itself. Okay, so I will go a little bit deeper into the like technical details of how exactly it works instead of this execution layer. So, like I said before, our input is interleaved image text tokens, which execution layer, and which this layer each layer consists of the language layer and the one image layer. So the input interleaved image text tokens will be fed into the both sides. But for the language layer, we use like a query tokens which only from the text set. So in this case, we will output like instead of output 6, we output 3 like blue text tokens. And for the image layer, we'll use the image as a query tokens, and we'll just output like 6 image tokens. And then we can just combine them together as output layer for this execution layer. So this design have some nice properties. So first of all, it's even though we like double the parameters, but we still have the like the same flops as like if you have a single layer, because we kind of separate the query tokens for different layer. And second one is also what I like the most is it can benefit from pre-trained models. So because this is kind of like a modular design, so from the left side, the language layer, and the right side, the image layer, they are kind of like a separate like operations. So you can just use any pre-trained language models or vision models. So what do I mean by that is if you think on the high level of our execution design, which is we have like a language tower and then we have the image tower. But in practice, when you train this model, you can just initialize those two towers with any like pre-trained models. For example, from the language side, we can use like a llama model. We can use like a crane model. And for the image side, of course, you can use again from the initialize from the language model like a crane. You can also initialize from other like image general models such as the stable diffusion or flux model. And also for the modeling, it's also flexible. For the image side, you can use a diffusion modeling or you can use autoregressive modeling. And also in terms of the training is also very flexible. You can just depends on what you need. You can just freely like choose to freeze one side, do the LoRa fine tuning for the other side, or you do the full model fine tuning for the other side and freeze some other from the other side, etc. So basically, this modular design gives you a great flexibility in terms of the initialization and the training. So as I said before, the Xfusion is a flexible framework for unified models where you can use any pre-trained models and training objectives. Here I show like four settings where like in each notation, the left side indicates like the language model we are using. So for example, here I show we are using the Llama model and also the Queen model. And on the right side, I have what is our vision model. So we tried we initialize from the Llama. We also tried the initial from the Queen or Stable Diffusion 3. And what is the bracket is a modeling for the image side. So you can see here we tried the diffusion and we also tried the autoregressive for the image. So the high level message here is that basically this design can give you any flexibility to train your or design your ML models. Okay, so except for architecture exploration, in this paper we also try to study the representation. Especially we study the synergy between the generation data and understanding data. So if you think about the image and text, if you think from the image perspective, we can categorize them as like image understanding data and also image generation data. So understanding could be something like what is the breed of this dog, and then it's a Shiba Inu, and or it's can you generate a photo of the Shiba Inu, and model can give you a photo. So basically, there are kind of these two main tasks when you think about the unified models. And we found out in our pre-training stage, actually the understanding data can help you the image generation. And this observation also observed in some recent other work. So basically, the reason why it can benefit the generation is because if you have a good understanding data, the understanding can learn a really good representation features, which will in turn favor your generation. But in this paper, we do not observe the other way. Basically, we did not observe image generation help the understanding. But personally, I believe the generation can help understanding. Probably because the current understanding focus too much on the high-level semantics. If we can have some way to measure the some low-level details about understanding, maybe I think the generation will help the understanding. And another example of the representation matters is a noise level when you do the pre-training. If you choose a transfusion modeling. So basically, in a unified model training, you will have a lot of interleaved data. So basically, in this example, you will have the text, you have the image, you have the text. If you just, for example, for this case, if you just think from the left side, basically that's just like an image generation task. It's text and followed by the image. From the generation perspective, of course, during the training, you want to sample all the noise to cover all the sample steps during the to train the general models. But if you look at the other side, basically this is image understanding task because this is first started with the image and followed by the text. But for this task perspective, you also do not want to have a lot of noise for this image because you can imagine if you have a pretty noisy image, you're asking model to do the text hallucination. So basically, there's a contradictory for the noise level for training those interleaved data. So one side we want to have all the noise, on the other side we do not want the noise. So basically, in the training we found out the best way to train your unified model is you just repeat your image twice. So basically, you separate the generation on understanding differently. So for the first repeat, you just add whatever the noise you want to train your generation. And for the second repeat, you just use a clean image. So basically, this is kind of indicates if you use a clean image, you can yield a better representation, which will in turn favor your generation. I think this kind of a technique is also used in the recent a Bagel paper from Bedons. Okay, so like any other like unified models, after pre-training, we can also fine tune on some like a downstream tasks. And here I will just quickly show some like a downstream results. For example, you can do some like a text to image generation. And here are the results about the like semantic understanding of a text. So basically, ask which fruit associated with the gravity, so it's a generate apple. We also downstream fine tune on the object removal data, of like image of painting, and also we can do the VQA, also the like image editing or localization. So all those tasks is done by single unified models. Okay, so basically, this idea of using like a separate weights for different modalities is also has been explored in some recent concurrent work, such as MM fusion from the Meta, and also the recent like a Bakel paper from the Meta. So this indicates that shared parameters could be the future for the architecture design for the unified ML models. Okay. So that's all good. Like if we suppose we have like a really good like unified models, it can do everything for you. Like you can ask the model to generate a photo of a dog for you, and the model can generate a nice dog for you. But if you ask another question, can you generate a photo of a bird for me? So the bird here is a dog name of our one of author. So basically, without any like personalized knowledge, of course, the no model can help you to generate like accurate like image for you, because the model is just trained on the like internet data. It has no like personalized information. So that will motivate us to the second part of the talk, which is how to personalize your ML models. And we found out actually the soft prompting is an effective way to personalize your ML model.
Just unmute you.
Oh, I see.
So now I will talk our series of works about the personalization. So specifically, we want to talk about how can we let your ML models understand and generate your personalized concepts. So the problem setting is very simple. So suppose you have like a few photos of your personalized objects, such as your dog named Bird, and we want to personalize your ML models into some like concept identifier, such that after personalization, you can do some like text like conversation. You can do pure text conversation, such as I want to buy a gift for Bird, like any suggestions, or you can do some like a visual question answering what it's doing here. So of course, without personalization, like all the unified model will fail for those tasks. Of course, like you can also do like personalized visual generation, such as generate photo of for example, boys reading books. So that's basically our problem setting and what we want to do. So how to do that? There's one very naive baseline, which is you can just use like a human written prompts to describe your personal objects. So in this example, you can just say, "Oh boy, like a Shiba Inu looks like a small fox, like a dog with an orange coat," and you can just append this prompts like into your system prompts. But there's an issue for this approach. First of all, it requires it requires like a human efforts for like you need to kind of like describe your objects every time whenever you have some objects you want to personalize your models. Secondly, is the human like the language prompt is will be pretty weak. It cannot like capture all the visual details. So like the prompt I read here, basically this is prompt is universal true for all the Shiba Inu. So but instead we want to like just like personalize that specific thought. So how do we do that? Is like we propose to use a learnable prompts. So basically, instead of using the human read prompts, we just say bird is and we train us like a k like a learnable tokens, like token one to token k's, and then this will be we can automatically train and also will capture more precise details compared with human written prompts. So on a high level, we just like in your like ML model vocabulary, we just add a new like k+1 new trainable tokens. So one is your identifier token, which is called and there are k learnable tokens to describe the feature details, like visual details for that object. And to make sure your model can learn the personal concepts, we found out actually the hard negative samples are really important for personalization learning. So basically, we during the training we retrieve a lot of like hard negative samples, and those negative samples is important because it can help you to define your personalized the representation boundary for your objects. And during the training, we will just treat all those as negatives, and those are positive. So we will do some classification tasks. And also those negative samples can also help you to learn the generative features. So basically, we can just rank them based on the visual similarity. The least similar retrieved images can contribute to some cross-level feature, and also the most similar one can contribute to some fine-grained details for the visual representation. Of course, I will just give some high level how exactly train. I will just leave the offline a talk. Okay, so after learning the this personalization about models, we can just do a personalized, for example, the text conversation. You can ask what should I pack for when we want to travel, and your assistant model can just help you to answer that question. You can also do some VQA tasks. For example, describe this image, then this model will know this dog is called Bobo, and instead of will misunderstood this a cat. And of course, you can also do some image generation tasks. For example, you can generate your personalized objects with in different settings. So those are 4 different generated results. Okay. I think I will. That's the kind of main topic about the today's my works. And next I will talk about the some open questions and some future directions. So I think the important thing nowadays we all know is the data. So basically, what is important next is or the open question is do we need large scale hard data? Nowadays, we have a lot of tons of data, especially in the image and the text domain. We have a lot of image text pair. But I will call those is a simple data. So do we need large scale hard data? So by hard, it can be multi-dimensions. So for example, do we need large scale personal or long tail distribution data? Or do we need other large scale data in other modalities instead of the text and image, such as we probably also want a lot of data in 3D physics or other sensory inputs. But how do we have them is also a problem. Also, do we need domain expert data? So now we have some domain expert data in the NLP, such as we have the math problem, we have a coding problem, but do we need to go beyond those 2 domains? Also, once we have all those data, how can we just connect them to better learn the representation? And also, will the current approach scalable on those hard data? That's also, I think, is an important question. And lastly, the question is, for the unified models, we have different modalities, but will all the modalities share the same representation, or will they kind of partially share some representations? So some interesting question is, suppose we have some shared representations, then how can we freely encode one modalities and enter into the representation and decode it back to the other modalities? So basically, I think those are kind of really interesting and important future directions. Okay, I think, yeah, that's basically the end of my presentation. And thank you all the authors and collaborators in this 3 work. And yeah, if you are interested in those works, you can just scan the QR codes for the project page, or you can attend today's poster session. Yeah, I'm happy to take the questions from